I have with me today Tom Schriber, who's Professor of Business Information Technology in the Stephen M. Ross School of Business at the University of Michigan. He is the recipient of the Informs Simulation Society's Lifetime Professional Achievement Award and of the Society's Distinguished Service Award. He is a fellow of the Decision Sciences Institute and author of 4 textbooks, among them Simulation Using GPSS and Introduction to Simulation Using GPSS-H, which were in widespread use for many years in this country and abroad. He served 10 years on the WSC Winter Simulation Conference Board of Directors and was board chair for 2 of those years. At the 40th anniversary of the WSC, his co-authored paper, Inside Discrete-Event Simulation Software, How It Works and Why It Matters, was designated as one of the 10 landmark papers given in the first 40 years of the conference. He is a charter member of the Decision Sciences Institute and is a member of ASIM, the German Language Simulation Society, the Institute of Industrial Engineers, and Informs, and is listed in Who's Who in America. His research interests over the years have focused on discrete event simulation and include the logical foundations of discrete event simulation software, design of discrete event simulation experiments, analysis of discrete event simulation output, and the use of discrete event simulation for decision support, such as the design of manufacturing systems. On a personal note, in 1986, I had the privilege of attending Tom Schriber's class on GPSS-H, and the insights that I gained during that class really were the genesis, or started my work as a simulation software developer. So, Tom, I'm going to turn it over to you at this point.
I can try to deny everything that you said. Thank you very much. Tom Schriber here, sitting in Ann Arbor, Michigan, the home of the University of Michigan, and with the great pleasure of being able to conduct this webinar. Some people, I believe, are still signing in, which is fine. I would like to start by thanking Dave and also Jeanette, the organization, Dave's organization, for suggesting this webinar in the first place and providing me an opportunity to present it. The presentation is based entirely on PowerPoint slides. That's what you see. My understanding is that you see these on your screen now. This work is a co-developed work with Dan Brunner. Dan is a former student in the program here at the University of Michigan in grad school. He's currently, as you can see, with Kiva Systems in Woburn, Massachusetts. Okay, so we bypassed the poll that was really designed to probe the extent to which, probe your background with respect to discrete event simulation. This presentation might strike you as a little bit of a hybrid, because we start by choice in quite fundamental terms that might be too fundamental for some of you, and then we ramp up from there, and we wind up with considerations that in fact might not be immediately clear to some of you, that might require some reflection, some review perhaps after the fact of these slides and what have you, and also call for what I would term deep diving into the internal characteristics of whatever discrete event simulation software package you happen to be using. So the objectives here are to introduce for some and review for others some features of the underlying foundations on which discrete event simulation software is frequently built, and to try to sensitize you to the relevance of material of that type. Additionally, to try to motivate you to gain a working knowledge of particulars such as we'll be discussing in the setting of whichever modeling language you use or are considering using. And ultimately, the goal, of course, is to enhance the skills that you personally bring to bear as a professional designer, implementer, and user to support decision-making of discrete event simulation models. So, an outline here, we'll say some things about the background that motivates this presentation in the first place. Then in terms of discrete event simulation, we'll talk about something called the transaction flow worldview, the implications for the nature of discrete event simulation, and some generalized comments on discrete event modeling languages. We then will present a generic description of the requirements of discrete event simulation software, not referring to any particular implementation, using vocabulary we introduce for that purpose is listed there. We will then, still in generalized form, do an overview of model execution in terms of some of the items listed there. We will then talk about what we call entities and the various alternative states through which entities migrate over time during their the lifetime they experience moving through a discrete event simulation model. We'll then consider the management structures that have to be put into place to manage entities as they wend their way through their lifetime in a model. Then we will illustrate specifically, we only really have time to illustrate in terms of one language, and that will be GPSSH because of its nature as a classic discrete event simulation language going back to IBM many years ago. Still a very good worldview, and then call your attention to the fact that similar considerations are available for each of 5 other languages in literature that we've provided. We'll then talk about why it matters in the first place, why it can be dangerous to simply use discrete event simulation software in black box fashion, making what can be the naive assumption that the software is behaving the way you might believe without verification that it is behaving. And then we'll do a summary. This is a rather lengthy presentation in the context of the annual Winter Simulation Conference, which focuses on discrete event simulation and takes place each December. The next one will be in December of 2012 in Berlin, Germany. This will be the first time that the conference has taken place outside of the United States, actually. The presentation is designed to last 90 minutes. Here, because of the nature of the webinar, we've asked you to slot on the order of 2 hours of time if you can stick with this from beginning to end. So the background approach is, if you've had an opportunity, for example, to take a credit course in the context of a degree program, a credit course on discrete event simulation, often the internals of the software are not included as part of the course, resulting in a black box approach really to use of the software. Told in broad terms, sure, what the software does, but the subtlety, the potential subtlety of interactions of elements in the software might not be explored. In the interest of saving time, you just can't do it all in a 3-credit course. Simulation really as a concept is like a broad umbrella that encompasses many subtopics. One is, of course, simulation software, but another is design of experiment. Another is analysis of data. Another is interpretation of output. There's simply too much to do in a 3-credit course, to do comprehensively in a 3-credit course, and very few people have the luxury of taking a sequence of 2 3-credit courses on the topic of discrete event simulation. There are probably others among you who are self-taught in this area, which makes it even potentially more important to hear material of the type we're talking about now. As we move along, a lack of knowledge of these subtle interactions might put you as a model designer into a situation in which you're not able to think things through when faced with needs such as developing good or even correct approaches for modeling logically complicated situations. And also of extreme importance, might put you in a position where you don't monitor the execution of your model interactively to troubleshoot error messages that might be being issued while you're still in the model development phase. And even after a model has been, to the best of your knowledge, completely developed and is operating the way you intend to in terms of the logic that you've captured with the model, you might not then be using interactive tools to verify that complex system logic has been accurately captured in your model. Okay, so these are some of the considerations background-wise that led Dan Brunner and me some years ago to develop this presentation, and the presentation has evolved, over time necessarily as our insights have grown and as the needs of practitioners of discrete event simulation have come into better focus for us. Okay, let's talk about what's termed the transaction flow worldview. It provides a framework on which a lot of discrete event simulation software is based. And again, what's a worldview? A stylized way of looking at a situation. You put on your worldview pair of glasses and you see the world through that worldview. Sorry, my phone is ringing here. I'm not going to pick it up, of course. So the German word for worldview is Weltanschauung. So in the transaction flow worldview, a system, or in some sense maybe the world, is thought of as consisting of discrete units of traffic, often described with the word transactions, that compete with each other for the use of resources, typically scarce resources, while moving, flowing in some sense, from point to point in the system while time elapses, while time goes by. That word flow in the context of discrete event is perhaps not the best word. Flow implies, to me at least, something continuous, such as the flow of water out of a faucet, whereas we're talking about what we might think of as relatively jerky movement of transactions of entities of discrete units of traffic from point to point. So because resources are typically scarce, they often don't have enough capacity to respond immediately to all the demands placed on them at a given time. And this means that some transactions must wait their turn, queue up, if you will, to use resources that other transactions currently have under their control, making them unavailable to some requesters. So we're going to consider several examples here. Now, please don't be put off by what appears to be the relative simplicity of these examples. This sets the stage for later discussion. So we start with as an example, with a rather homely one-line, one-server service point in a system, where you can see that we have a server. The server's in a state of capture. The capturer is represented by this white circle here, and we have this is the transaction or unit of traffic that currently has the server in a state of capture, and we have arrivals to this point. We have other units of traffic waiting their turn to use the server. Now, this actually feeds into what was intended to be the first poll question. Have you ever built even a very simple discrete event simulation model from scratch using a general purpose language, such as, say, C++? If you have, you might remember that without experience, you've got your work cut out for you. consider some of the complications that can occur in a situation like this. How is the waiting line arranged? Is it simply first come, first served, as it might be in a public system of some kind, or is it first come, first served within priority class? Are there priority tags attached to various units of traffic here, meaning a fresh arrival might cut into line ahead of some others who were there ahead of that arrival? What about balking? Balking occurs when some unit of traffic says, I waited long enough, I'm not going to wait any longer, I'm going to move to some other point in the system. What about preemptive use of the server? What if a unit of traffic comes along that is so important that it is privileged to displace the current unit of traffic from the server, even though that current unit of traffic is not yet finished receiving service, and then immediately take over the use of the server resource, so-called preemptive use. So even a one-line, one-server system like this is capable of being quite logically complicated. Moving up the chain a little bit, consider a one-line multiple server service point. The same considerations hold in terms of things like balking, prioritized waiting line, potential preemption, the possibility that your servers are not homogeneous with respect to each other, even though they provide presumably a common type of service. They might be heterogeneous with respect to each other, and so it's important in that case for the logic of the model that the unit of traffic knows which server in the set of servers it has taken control of. There's also a possibility that a unit of traffic might require the use of two or more servers in a pool of similar but not necessarily identical servers. And then, continuing to expand, you can talk about a multiple line, multiple server service point. All of the considerations mentioned for each of the first two apply here. In addition, here you have the possibility of line switching. You wind up in a queue in a line that's not moving as quickly as a neighboring queue, and you decide to cut out of your line and go to the back of the line that's moving faster, additionally adding complications. So if we think of each of these types of service points as basically a module or a component in a larger scale system, we might consider a system such as this one that we'll refer to frequently here during the course of the webinar, a system that's easy to relate to and that motivates the choice for such a system in at least relatively simplified terms. So here we have a harbor system representation where we have two different types of ships coming to the harbor, type A ships, type B ships. We have a series of berths in the harbor where a type of berth corresponds to the type of ship that that berth accommodates. So the implication is type A ships can only use type A berths to either load or unload cargo. Type B ships can only use type B berths. Now notice that these berths are resources. They are, in the physical sense of the word, fixed position resources. There is also the possibility, of course, of mobile resources, such as the set of 3 tugboats represented here. So the tugboats are resources, but they don't occupy a fixed position in the system. This can lead to the need to know where a tugboat is at a given time to determine the travel time from its position to, let's say, a ship that has arrived at the mouth of the harbor and is out there in open water waiting for a tugboat so that it can be tugged into the harbor. What's more, the number of tugboats required by a ship may depend on the type of ship, whether it's type A or type B, and might additionally depend on whether that ship is being tugged into berth, where there are alignment problems to take into account, or in simpler terms, having finished the use of a berth, is being tugged out of the berth, eventually finding its way into open water where it can proceed on its own. Another possibility for a scarce type of resource is space. So space can be a scarce resource. What if the mouth into the harbor is narrow to the point that only one ship can pass through at a time in either direction? Only one ship currently moving in, or alternatively one ship currently moving out, but no two ships in that mouth at the same time. And then you have to consider the possibility of staging space internal to the harbor. You could have a model freeze up, if you will, if all of the berths are occupied by ships that have finished the use of the berth, and yet there is no space to deberth into because all of the spaces here are occupied by ships waiting to move into a berth. That can result in a system freezing up. And so that is the idea behind having a representation here of what we call a dedicated space, so that there will at least eventually always be a space into which a ship can move from the berth to avoid system freeze-up. How about that? I mean, simple system. You can think of it as consisting of modules of the type we just talked about, and yet life can get rapidly very complicated in a situation such as this. Now, some of the issues that we might want to investigate by modeling this system would be what is ship turnaround time? As a function of ship type, what's the behavior of the elapsed time random variable that measures time between arrival of a ship of a given type at the mouth of the harbor on the one hand, and then eventual departure of ships of that type from the harbor, that is back out in open water and on their own steam, given that they've received the service they've come to receive. And then for, let's say, a given existing harbor that we might model, we might use the model to investigate the influence on ship turnaround time as a function of ship type. If we add, say, another type A berth, or another type B berth, or another berth of each type, or widen the mouth into the harbor so that two ships can be moving through the mouth at the same time, or change the number of tugboats in the pool of tugboats that service ships at the harbor. This sort of thing is really, what it's all about. It's what-ifing, if you will, what-ifing supported by model execution. Now, the nature of discrete event simulation. An event is a happening that changes the state of a model or changes the state of the system being modeled. Examples of events would be a ship of a given type arrives at a harbor. A ship captures a tugboat. A ship frees up a tugboat. A ship leaves the harbor. These are examples of events. A discrete event simulation, then, is one in which the state of a model changes at only a discrete and typically random set of time points that are known as event times. Now, you might say, but wait a minute. After a ship captures a tugboat, time has to elapse while the tugboat moves the ship to its destination. How do you model that using a discrete event worldview? Well, you do that by decomposing that movement process into two events. A starting event and a finishing event. So yeah, the position of the ship in that example is changing continuously over time. But you model the start of the change of position, and then you model the conclusion of the change of position. Change initiation, change completion. So loading a ship with cargo. You have a start to load the cargo event. After that event takes place, your model puts the ship entity into a state of suspension, waiting for the point to be reached in simulated time at which the loading process has come to completion. At that point, the software takes the ship out of a state of temporary suspension and puts it back on the move, moving through the model toward whatever is next in line for it. So what really happens in the context of discrete event simulation is that as part of the event start to load the cargo, a sample is drawn from the distribution, from the applicable distribution of cargo loading time. Cargo loading time might typically be a random variable. Probably it is. So a sample is drawn from the distribution of cargo loading time, and that sample value is then added to a copy of the simulation clock at that point in the simulation for purposes of computing the future simulated time at which that loading process will be completed. And the corresponding ship entity is then put into a state of suspension through that many units of simulated time. Now, there can be two or more events that take place at one and the same simulated time. Examples would be 1 unit of traffic involved, a ship captures a tugboat. That's an event, but the ship then initiates the process of getting tugged into berth. That's also an event. And if you don't model a time lapse between the capture event and the initiate the process of being tugged into berth event, you have those two events occurring at one and the same simulated time. An example for 2 units of traffic might be as follows. A ship finishes using a tugboat that had just pulled it into berth. That ship then initiates on its behalf a cargo loading process. Another ship then captures the tugboat that has just been freed up and initiates the process of using the tugboat to be tugged from point A to point B. How about 3 units of traffic involved? Suppose the ship has 2 tugboats under its control. It finishes using the 2, it frees them up, it then leaves the system, leaves the model of the system. The second ship that just needs 1 tugboat and has been waiting for 1 tugboat then captures one of the 2 that have just been released and initiates the process of using it, and then a third ship, also having been waiting for a single tugboat, captures the other tugboat that was freed up and initiates the process of using that tugboat. So this sets up a situation in which 2 or more units of traffic often have to be manipulated at one and the same simulated time point. That's achieved by having the software deal with units of traffic one after the other at that simulated time point. So we have a situation like this. We have a point in simulated time. Here we have a real-time axis. Here we have the same point in simulated time. Suppose 3 units of traffic have to be dealt with at whatever simulated time this is. So the software deals at first with one of the 3 units of traffic, then it deals with another one of the 3, and finally it deals with the last of the 3. So you have a chronological order in which units of traffic, each of which says, pay attention to me now, pay attention to me at this simulated time. You have a chronological order in which those requests to be paid attention to are handled. And the order, the real-time order in which the entities with their hands up are responded to, that real-time order in many cases makes a difference in model behavior, and is something that you need really in general to be sensitive to and to know how to control. Okay, so now if we think in terms of simulated time, in a discrete event simulation, simulated time does not elapse continuously. It elapses in discrete steps. So suppose that when a discrete event simulation starts, the simulation clock registers a value of 0, which is typically the case. At that point, the software deals one by one with any units of traffic that need to have attention paid to them at that simulated time. When there are no more units of traffic to be processed at the current simulated time, the software then advances the clock, advances the simulated clock to the next earliest point in future time at which an event, at least one event, has been scheduled to occur. For example, it might be that the first arrival of a Type A ship in the harbor model occurs at simulated time 15.2. The software then updates the state of the model at the newly established simulated time, and when that model date has been fully updated, the software then again steps into the future, steps to the earliest point in future time at which at least one other event has been scheduled to occur. For example, maybe it's completion of a cargo loading process that has been scheduled to occur at simulated time 32.7, and so on. So we'll say more things about this. The point here is that we're dealing with discrete points in simulated time, and that they typically vary at random, and that the simulated clock is monotonically increasing in value. The software does not set the clock back to earlier time to make amends for something it might have overlooked at earlier times. Hope I'm not being too obvious here. Okay, so the real-time order in which events are carried out at a given simulated time. Often, simple logic dictates the real-time order. For example, a tug has to be freed up before another ship can lay claim to it. So if those two events occur at one and the same simulated time, it's the freeing up of the tugboat that clearly has to precede the capturing of the freed up tugboat on the part of another ship. Logic does not always dictate the real-time order, however. For example, suppose orders arrive in a batch in an order processing system and are then to be routed into the order processing system without simulated delay. Then the question is, in what real-time order are they going to be routed to processing points? If 2 or 3 of them are being routed to a common processing point, then the first one to be paid attention to will be the first one to be dealt with at the processing point. Is that what you want? Do you want some other effect? How about 2 types of ships arriving at the harbor at the same time when there's one idle tugboat and each of them needs exactly one tugboat? Which ship gets the tugboat? How about a ship arriving when another ship finishes loading cargo? So each of the ships wants a tugboat. One to get pulled into harbor, the other to get pulled out of berth. Which one gets the idle tugboat? So the need can be set up to control the real-time order in which events are caused to occur. Events that have identical event times are carried out. We simply have to be sensitive to that possibility, and we need to know, if the occasion arises, how we can control real-time order to achieve logical effects that are consistent with what we understand the logic to be of the system that we're building a model for in the first place. Okay, that discussion has been with respect to the builder of a model, a person presumably using discrete event simulation software. So the challenges faced by the user really escalate for the person who has to design a discrete event simulation language in the first place, designing it in general purpose terms, general purpose with respect to discrete event simulation. So a designer must take the logical requirements of discrete event simulation into account in a generalized way and develop semantics and syntax that hopefully are easily understood by the modeler and also easily applied, while providing a user interface that facilitates the process of model building. And in that process, the designer of a discrete event simulation language, from time to time, perhaps rather often, faces the need to make a choice among alternatives. Some choices are made one way by a given designer of one language and maybe made in another direction by the designer of some other competitive language. This leads to a situation in which languages, similar in broad terms, sure, can easily differ from one another in subtle but important particulars. Okay, now toward a generic model. This is the vocabulary that we use for a generic model. Entity. We reserve the term entity for unit of traffic, or if you think of transaction worldview, a unit of traffic is described in that set of words as a transaction, such as a ship in a harbor system. Resource, a system element designed to provide service when requested by entities to provide service, like a berth in a harbor system. Control element, construct used to represent control-related aspects of a system state, or if you will, of the state of a model of a system. Examples would be simple on-off switches, or counters, or arithmetic expressions that can be tested to see if their value, say, has reached or exceeded a given level, or Boolean expressions that can be tested to see whether a Boolean expression at a given time is true or false. Operation denotes a step or action carried out by an entity or possibly on an entity. Ordered set of operations, a sequence of consecutive steps taken and/or actions experienced by an entity as it moves through a system. Sometimes that's referred to as operation logic. For example, consider a ship working its way through a harbor. Operation logic might take this form. The ship arrives at the mouth of the harbor. Then the ship, possibly having to wait, eventually captures a berth of the type it needs. Let's say lays claim to a berth. It's still out in the mouth, but it wants to establish for itself a destination that it can move straight to when it moves into the harbor. Then, let's say the ship needs 2 tugboats to be pulled into the harbor and appropriately aligned to move into the berth. It then gets pulled into the harbor, into the berth. It frees up the 2 tugboats. It doesn't need them while it's loading or unloading cargo. It then experiences the loading or unloading of cargo. It then, let's say, needs only 1 tugboat for deberthing purposes. After possibly waiting, it claims a tugboat. See, I've got deberthing misspelled. Gets pulled out of the berth, frees up the berth, moves out into open water, frees the tugboat, goes on its way, leaves the model. That could be the nature of the operational logic applying to an entity. In fact, notice one of the things that's true about entities moving through a model. The number of entities in a model at any given time is typically a random variable. Entities experience a birth process as part of being injected into a model, and eventually, in most cases, they experience a death process when they leave the model. So there's birth, lifetime, and death. Now, external versus internal entities. The designers of a DES, discrete event simulation language, clearly have to incorporate data structures and processing algorithms into their software for the purpose of managing entities. They sometimes are motivated to use those structures on a behind-the-scenes basis to accomplish various internal needs in modeling. Internal to the logic of a model, if you will. For example, behind-the-scenes entities are sometimes used to control things like machine breakdowns, to trigger shift changes, to bring an ongoing simulation to an end. We refer to that use of entities, or entities used for that purpose, in a behind-the-scenes sort of way, as internal entities. Now, I'll tell you, the reason you need to be aware of the possible existence of internal entities is because if you ever, in interactive mode, let's say, look at a list of entities currently in a model, you've got to be able to distinguish between entities used for internal purposes, such as mentioned here, versus those used as external entities, that exist as external entities. The entities that you use to simulate actual units of traffic in the system, we think of those as external entities. They're the ones that you think in terms of. Now, you might use entities in ways other than to represent units of traffic. A very useful part of discrete event simulation often can be to put watchdog entities into a model for the purpose of monitoring model conditions and controlling model response to changing model conditions. I think watchdogs is a good word. Watchdog entities might be introduced into a model at simulated time 0, put into their positions from which they do their watchdogging, and never leave the model during the course of a simulation. So they experience creation. They don't eventually necessarily experience destruction. I think of those as the entities in which the modeler thinks and plans the design of a model. Now, sometimes if internal entities are not provided as part of the simulation software that you're using, you encounter situations in which it's convenient, maybe even necessary, to use what we think of as external entities to play the role that might otherwise be played by internal entities in some other software choices. Okay, now let's talk about a possible experimental design here. So let's say as a simulation project, we want to model an existing harbor. We want to measure ship turnaround times in the harbor as a function of ship type. In the harbor as is a function of ship type. Let's call the harbor refer to the harbor as is as alternative 1. Then experiment 1 in terms of alternative 1 might consist, if you're using something called the method of replications as your design of experiment, might consist of carrying out a series of replications as indicated here, where the only difference from replication to replication is, as indicated here, that random numbers differ from replication to replication. So you're simply rolling, the dice are being rolled differently, resulting typically in different results. And so you build up a sample of observations of, if you will, average ship turnaround time. Computing the average ship turnaround time, maybe it's standard deviation, it's minimum, maximum, and so on, for each replication in the series. Suppose you then say, okay, I'm going to move on to another alternative structuring of the model. I'm going to take the model as is and supplement it by adding, say, an additional berth for type A ships. And then for that alternative 2, you proceed to carry out a series of replications. You then keep this process up, considering or measuring the impact of various alternative ways to expand the resource set at the harbor and what influence each of those alternatives has on the performance of the harbor in terms of ship turnaround time. Okay, so that might be the big picture in terms of something you propose to model in the intended use of the model in the first place. Okay, now we want to get into the anatomy of just one of those replications, representing it in flowchart form, very macro flowchart form, this way. So let's say the simulation clock starts at a value of 0. And in the process of initializing the model, initial events such as arrival events, say the first arrival of a type A ship at the harbor, the time of that first arrival, the time of the first arrival of a type B ship at the harbor. Then if there are any events that might be scheduled to take place at simulated time 0, then those events are carried out at that current simulated time 0. Maybe in the harbor model there are no events that would take place at simulated time 0. This overall process of executing all possible events at the current simulated time, we give the name entity movement phase, the EMP, entity movement phase. The simulated clock is standing still, real time is elapsing, while the state of the model is being updated at whatever that simulated time is. Then the software steps into the future. It advances the simulated clock to the earliest point in future time at which at least one event has been scheduled to occur. We refer to that as the clock update phase, the CUP. And then after the clock has been advanced accordingly, then at the newly established simulated time, looping back here, in the next entity movement phase takes place, updating the state of the model at the freshly established current simulated time. And so for the most part, we simply have a looping process here taking place between an entity movement phase on the one hand and a clock update phase on the other hand. So this whole process continues with statistics. This looping continues with statistics being observed depending on how you've designed your model and so on, until finally an ending condition is satisfied. It could in general be satisfied during an entity movement phase, or it might be satisfied as a result of a clock update phase. But once the ending condition has been satisfied, then the movement of entities stops and the software goes, in general purpose terms, into a reporting phase, reporting out the results in statistical terms to you. So then, in effect, the essence of a run, the essence of a replication, is represented here in this fragment of a flowchart: the entity movement phase and the clock update phase. In fact, if you deep dive into the internals of the software you're using, that deep diving will have the objective of putting you into an understanding of how the entity movement phase proceeds with the software that you're using, and then how the clock update phase proceeds with the software that you're using. The clock update phase can be relatively simple. The entity movement phase can be potentially very complicated. Okay, now your entities, your units of traffic, your transactions, if you will, during the course of their lifetime in a model, they migrate from entity state to entity state, not necessarily in any fixed sequence for each of them, but depending upon the role being played by the entity in the model, where it is in the model, what its needs and wants are, what its next set of needs and wants are, what alternatives it has for path selection moving through the model. First of all, in terms of entity state, there is this what we call the active state. It is the state of the moving entity, if indeed at that point in the simulation there is a moving entity. Remember, the software is only paying attention to one entity at a time, trying to push one entity at a time forward to the extent possible in the model from wherever its current position is. A second entity state is what we call the ready state, the state of entities that are waiting to enter the active state at the current simulated time. So what you see through the ready state is the possibility that two or more entities want to have the software pay attention to them one by one at the current simulated time. You've got the one entity that is being paid attention to by the software, and you've got the other entities that are in line saying, hey, you know, I'm here too. Don't forget to get around to me before the next clock update phase. Then there is the time-delayed state. State of entities waiting for a known point in simulated time to be reached so that they can be put into the ready state. They are ready to be paid attention to again. The time-delayed state, for example, would be the state of a ship which, having been moved into a berth, is put into a state of suspension. That's the time-delayed state. Well, a known amount of simulated time, that would be the sampled simulated time required to load or unload cargo for that ship. Well, that known amount of simulated time elapses. Then there is the fourth state, condition-delayed state. The state of entities waiting for the unknown simulated time at which some blocking condition that they're experiencing, some delay-inducing condition, will be resolved. For example, ship is at the, has arrived at the mouth of the harbor. it's waiting to claim from a distance, if you will, the use of a type B berth. It doesn't know at what point in future simulated time a type B berth will be freed up by some other ship. In that sense, it's waiting for the unknown simulated time at which the blocking condition that's experiencing will be resolved. Now, as indicated here, the software, the discrete event simulation software at the level of the language itself, can be designed to be intelligent enough to automatically transfer entities from the condition delayed state to the ready state at the right point in simulated time. The modeler does not have to provide the logic needed to bring about that transfer. However, to provide flexibility in general for the model builder, there is the possibility of a state that we call the dormant state, the state of entities waiting for the unknown simulated time again, at which a blocking condition they're experiencing will be resolved. And then if the dormant state is used in the modeling process, it's the responsibility, of course, of the modeler to supply the logic needed to transfer such entities under the right conditions from the dormant state to the ready state. Oftentimes a watchdog transaction will be used to monitor the situation and bring about the transfer that's implied here. We'll have an example of that toward the end. Okay. I see, by the way, for what it's worth, that since I started talking, we are 55 minutes into the presentation. I think what we will do for your sake is take a break after we go through what we're doing right now. Maybe take a 10-minute break, give you a chance to fill your coffee cup again. Okay, this is kind of a favorite diagram of mine in this in this whole set of PowerPoint slides. So here we have a representation of the active state entity at some point in an unspecified discrete event simulation. So the software is paying attention to it. And let's say it's a ship which has just been pulled into berth. And now the ship causes a sample to be drawn from the distribution of ship, I'll say, loading time. And that sample is used as the basis for computing the point in future time when the loading process just being initiated will come to a conclusion. So the ship transaction then is migrated by the software from the active state to the time delayed state, waiting for that future point in simulated time to be reached. When that time is reached, a clock update phase will transfer the ship entity from the time delayed state to the ready state, ready to be paid attention to during the following entity movement phase. Eventually, it will become, at that simulated time of loading completion, it will become the active entity. And the software will be focusing its attention again on that ship entity. Now, having finished unloading, the ship next needs to claim one or more tugboats for deberthing. Suppose the needed tugboats aren't available to it when first requested. Then the ship entity will be put into a condition delayed state, waiting for the unknown point in simulated time at which the needed tugboat or tugboats will become available to it. When that point in time comes, the software will transfer the condition delayed ship entity from the condition delayed state, as you can see, back to the ready state, so that at the simulated time in question, the software will eventually migrate from the ready state to the active state. The software will pay attention to it again. Now, a third possibility for movement from the active state is to move into what we describe as the dormant state. I mean, this is dormant, but with automatic reactivation, if you will, automatic return to the ready state. This is dormant as well, but with the user, the designer of the model, being responsible for controlling the eventual transfer or migration of such an entity or entities from the dormant state back to the ready state, presumably because the blocking condition they've been experiencing has been resolved. It might be a logically complicated blocking condition. It's been resolved, and now they are ready to take advantage of the fact that they're no longer blocked. Of course, we need the creation from time to time, the injection from time to time of entities into the model. So here we represent the point of entity creation. Now, typically an entity is created, let's say a type A ship arrives at the harbor. As part of that arrival process, the software, let's say, will schedule the arrival of the next type A ship, the successor to the one that's currently arriving. It will schedule that arrival by sampling from the distribution of times between consecutive arrivals of type A ships. Now, if the time lag elapsed before the next arrival occurs is greater than 0, that corresponding incipient arrival will be put into a time delayed state until that future point in simulated time is reached, when it will in fact make its appearance at the mouth of the harbor. If the time between consecutive arrivals turned out to be a 0, then the successor is to arrive at the same time as its predecessor arrives, that is, at the same simulated time. And in that case, that ship entity would be put directly into the ready state so that it can be paid attention to at that very current simulated time by the software. That's why you see two possible paths from the point of entity creation here. And then we have, of course, the representation of entities being removed from the model, entity destruction, if you will, birth events and death events. Of course, in a given model, you can have many different points where there are birth events and many different points where there are death events. In any event, anyway, it will be from the active state that an entity eventually moves in such a way as to cause itself to be removed from the model. Okay, now one more subtlety here in this diagram. In fact, in a live situation, I would typically say, okay, is there anybody out there who thinks that maybe there should be one additional arrow added to this diagram representing migration paths among entity states? And depending on the level of experience, some people, if you will, can make the needed suggestion. I'm going to add that arrow right now. This one might surprise you. Bingo. Let me add it again. Take it away, add it again. Take it away, add it again. I really want to emphasize this, obviously. It can be the case. Now, this gets into subtle modeling, and we'll have an example if you can hold on throughout this webinar. It can happen to be the case that the active entity, although not done with the set of moves it intends to make at the current simulated time, says to the software, put me down temporarily at the current simulated time. Put me back into the ready state at the current simulated time. I know based on the role I'm playing in the model that I have just made a move that's going to let other ready state entities successfully move forward in the model. Put me down, let them make their move, and then pick me up again. And I'm going to carry out a couple of additional responsibilities at the current simulated time. Let me give you just a very simple example in human terms. My wife, for example, is a great one for going to estate sales. She just loves to do that, and I think it's great. It's a lot cheaper than hiring a psychiatrist. Sometimes at estate sales, people are only let into a house in small groups, one group at a time. And the door is kept closed and is watched, if you will, by somebody who's hired to help conduct the estate sale. So suppose the number of people let into the house in groups of, say, 10, are let into the house in groups of 10. The person watching the door into the house is also watching the door out of the house. And when 10 people have left the house, this person then says, okay, the next 10 people in line can come in. This person opens the door for those people, stands aside while they shuffle through the open door one at a time until 10 of them have done so. And then this person says, okay, now I'm going to close the door again. Those of you still in line are going to have to wait at least until the next group of 10 can be let in. So that person controlling the door, watching the door like that, I would refer to that person as a watchdog. That person has a role to play. He's monitoring the state of the, if you will, estate sale. And by opening the door, he says, I now have made a move that I know is going to let some in the ready state also make a move. I'm going to stand aside, let them make their move, but when they've made their move, I want to be paid attention to again because I got to reclose the door. I basically opened the door, let some people through it, now I close the door. That is all taking place, let's say, in a model at one and the same simulated time. A little bit unrealistic in terms of the real system, but perhaps model for simplicity is taking place at one and the same simulated time. So that return arrow, take it away again, that return arrow can be a very important arrow in the context, or a very important migration path in the context of discrete event simulation. Boy, if you're on top of this diagram, if this diagram helps bring things into some degree of focus for you, if you haven't thought about things in these terms before, then boy, I think this is a great way to begin to pull these ideas together into a cohesive whole. Okay, about condition-delayed entities, simple delay versus compound delay. Some types of delay pretty clearly are or can be resolved by occurrence of a single or simple event. For example, one or more ships are waiting for a tugboat. The simple event of having some other ship free a tugboat resolves the delay for one of those waiting ships. That type of delay is referred to as simple delay because the resolution of delay of that type is easy to detect. And it's in those cases that the software can then bring about the migration of an entity from the condition delayed state to the ready state just by relating the occurrence of the delay resolving event to the need on the part of a condition delayed entity, sometimes referred to then as related waiting. Compound delay involves situations where single events don't necessarily bring about a resolution to a blocking condition being experienced by an entity. For example, suppose the logic of your harbor system is that a ship insists on capturing at one and the same time both a tugboat and a berth. The ship is out at the mouth of the harbor. It says, I need a berth, but I also need a tugboat to get pulled into that berth. I won't claim the berth first and then wait, if necessary, for the tugboat. I want to get the two resources on an all or nothing at all basis, for whatever reason that logic might be used. Pick off your resources simultaneously rather than sequentially. So the freeing up of a tugboat doesn't necessarily do the job. The freeing up of a berth doesn't necessarily do the job. So when you have compound delay like that, it's sometimes handled in software by taking what is called a polling approach, leading to the term polled waiting rather than related waiting. So in polled waiting, the software checks routinely at predefined points in the entity management algorithm, the updating of the state of the model, at a given simulated time, to see if compound delay inducing conditions have been resolved, and if so, takes appropriate action. Okay, entity management structures. Entities typically organized in lists. So if we use circles to represent entities, a list of entities can be visualized this way. If you will, a list is a chain, an open chain, a chain that doesn't loop back on itself. It has two ends, a top end, if you will, and a bottom end. So for the active state list, because at most there's only one entity at a time in the active state, this is not with regard to multiple core use. We don't bother to even give that list a name. The name we give to the set of one or more, if any, entities in the ready state, ready to be paid attention to by the software at the current simulated time, is current events list. The name given to the list of entities in the time delayed state is future events list. So those lists, those three lists, if you will, might be visualized as follows. So notice there's an ordering property implied for the current events list. There's an ordering property implied for the future events list. The future events list is usually arranged in order of increasingly later scheduled times for next attempted movement. We give the name delay list to the condition delayed list and user managed list to the dormant state of entities. There can be many lists of each of those two types in a model. For example, there can be a condition delayed list for each point of potential delay in a model. One list for ships waiting for tugboats, another list for ships waiting for type A berths, another list of ships waiting for type B berths, and so on. So in terms of those lists, we might have, say, a couple of delay lists, a couple of user managed lists, each with at least one occupant, maybe, as suggested here. So to summarize, entity states and entity lists: active list, active state, ready state, time delayed state, condition delayed state, dormant state. Now, we want to simply illustrate the macro logic of the entity movement phase and of the clock update phase in a choice of a language, and we are choosing here the general purpose simulation system software that was pioneer software of this type introduced by IBM. So we have similar coverage of other languages in material that has already been indicated. For example, the chapter in Jerry Banks' Handbook of Simulation published by John Wiley and Sons. I think that's referenced at the ExtendSim website, and also the proceedings paper that appears in the Winter Simulation Conference proceedings, and which is easily available. So in terms of GPSSH, external entities are referred to as transactions in that language. Internal entities are referred to as system transactions. Resources take two forms: facility, which are single servers, and storages, which are pools of similar servers. Control elements consist of logic switches, arithmetic expressions, Boolean expressions. An operation, that is a single step to be carried out by a transaction, is represented by a block. The current events list is called the current events chain in GPSS. Future events list is called the future events chain. The current events chain, interestingly enough, is also used to play the role of delay list or delay lists. That's done by endowing each transaction with an on or off flag. If the flag is on, the understanding is that the transaction is in a state of delay. If the flag is in the other setting, then it is in the ready state. User-managed lists are called user chains in GPSS. The entity movement phase is referred to as the scan phase. It involves the scanning of the current events chain. And the clock update phase is referred to as the clock update phase. So suppose we show how blocks can be used in this language to describe the operation logic in the context of the harbor model, such as Type A ships moving through a harbor. At the level of what is called a block diagram, the logic is as you see it here. So here's a point of creation of Type A ships. This is a description of inter-arrival time. It happens to be uniformly distributed in this case. This turns on a statistical clocking mechanism to measure time in port, to start tracking time in port for the most recent arrival. This turns on a statistics tracking mechanism relative to waiting for a Type A berth. Here's a request for a Type A berth. This block can deny entry from the queue block if there's no Type A berth available. As soon as entry is permitted, this updates the statistics tracking. That ship is no longer waiting for a Type A berth. Here's a request for a set of 3 tugboats on the part of the Type A ship. This block can deny entry. When the tugboats are available, the advanced block transfers the ship entity to the future events chain for the indicated amount of simulated time. That's the state of suspension while berthing time elapses. Then in the berth, the 3 tugboats are freed up. Here's a trip back to the future events chain while the state of temporary suspension while unloading time elapses. Here's a request for 2 tugboats to get pulled out of berth and back to open water. Here's a deberthing time back into open water, the freeing up of the two tugboats, the freeing up of the berth that had been occupied, that S should not be there, the updating of the time in port queue statistics, and the departure from the model by moving into a terminate block, terminate the existence of that transaction. So in practice then, the operational model is composed of the statement equivalent of blocks such as we're looking at here. The entity movement phase takes this form. I think we won't go into the details of that logic. The clock update phase takes this form, transferring of qualified transactions from the future events chain to the current events chain, poising them to be looked at one by one when they become the active transaction during the ensuing scan phase. And in terms of this diagram that we saw earlier, the series of discrete points in time registered by the simulation clock in a hypothetical simulation. At each time we have the entity movement phase followed by the clock update phase that carries the clock to the next earliest point in future time where something has been scheduled to occur, then the updating of the system at that state in time, then the next clock update phase that jumps the clock again, and this whole process continues until a simulation ending condition is reached, such as, let's say, the clock time having reached 5 days worth of simulated time. Okay, why it matters. The first kind of why it matters, monitoring model behavior. Boy, if you're not doing this, you are turning your back on a very powerful resource provided by Discrete-Event Simulation Software. Among the more powerful features, tools provided to interactively trace model execution, making it relatively easy for the modeler to engage in two extremely important aspects of model checkout. One is troubleshooting models, figuring out why error messages are being issued from time to time when you're in the model development phase, let's say. And the second is verifying models, that is, tracing, if necessary, at the level of step-by-step, tracing model execution to improve, to bring about a high degree of confidence on your part that entities in the model are behaving as you intended to have them, as you intend to have them behave under the conditions that are in effect in the model at the time the behavior is being witnessed by you. If you will, looking over the shoulder of an executing simulation and moving forward in the simulation only one step at a time, possibly only one step at a time. Step by step, you watch the simulation unfold. Does that ever add insight into the nature of a discrete event simulation and into the behavior of your model? Now, the types of things that you can do, you can set what some languages call breakpoints on blocks or their statement equivalent, so that whenever an entity is poised to try to enter such a block or execute such a statement, an interrupt occurs and you're given control at the terminal, at your monitor. You can then, if you choose to, display the current events list, the future list, delayed lists, user-managed lists, selected statistical information to gain insight into the state of your model. And you can set breakpoints also on entities. Not on all entities probably, that would be too much, but on some key entities. I think of it as putting radioactive isotopes into a biological system. You set breakpoints so that whenever an entity that has a breakpoint set on it becomes the active entity, and it's poised to start trying to make its next move through its next several steps. An interrupt occurs, and you're given control at the monitor, and you can look around display lists, display statistics, look at the next block attempted by that entity, look at the block the entity is currently in, and you can set breakpoints on simulated clock times too, so that whenever a given simulated clock time is first reached or possibly is overshot, because not every potential clock reading will be realized, bingo, an interrupt occurs in your given control. So that type of interactive monitoring really involves a conversation between you and the monitoring software. If you don't speak the vocabulary of the monitoring software, you can't have as meaningful a conversation with that software as you would be able to have otherwise. So the effect can be to discourage using interactive model checkout, and that would be a real shame. Yeah, it hurts a little bit at first, to tell you the truth, to dig down into to deep dive into the particulars, the internal logic. So a second kind of why it matters, you sometimes have to understand model behavior. I should say the possibilities for molding model behavior to achieve the kind of logical effects that you want. Because there are no, if you will, standards that language designers are forced to follow. Superficially identical models built using differing software might not behave identically in all situations. So we're going to look at three types of situations in which understanding the internals can matter. For example, when the active entity decides to request a resource that it has just released, just put into an idle state. When the waiting condition for the highest ranked entity in a delay list has not yet been resolved, whereas the waiting condition for a lower ranked entity in that same delay list has been resolved. And finally, when the active entity needs to yield control temporarily to one or more ready state entities by going back into the ready state itself, and then regain control at the same point in simulated time because it still has tasks to perform at that simulated time. So for this first situation, if you consider a flexible job shop, and if we assume that when a job finishes a task on a given machine, it frees up the machine and then scans the situation in the interest of obtaining the best machine it can obtain for whatever the next task is to be performed on the unit of work in process. What if the most suitable machine for the next step turns out to be the machine that the job just released? What if other jobs are waiting for that machine? What if all those other jobs are less qualified for the machine than the job that just released it? In that circumstance, will the releasing job be the one to recapture the machine? Or the other side of the coin, if a more qualified job is waiting to use the machine, will it be the one to capture the machine rather than the job that just released it? So of interest here is the real-time order in which updates are applied by the software in connection with the freeing up of a resource and the next capture of the resource. So here we have our simple representation again of one line, one server. We have a situation where the active entity is the entity controlling the server. Put on the move, it says I'm done with the server, and makes a move to put the server back into an available state, back into an idle state. What happens next then? Is this entity put into a state of suspension and waiting work in process job is given control, and then the forward motion of this entity is resumed? Or is this forward motion continued until it can move no further, and then action is taken to put a next entity or another entity or an entity into control of the server? So when does the entity that's releasing the resource become, in operational terms, a contender for the released resource? At least three logical alternatives here. When is the successor for use of the machine chosen? One possibility is at the very instant that the resource is released. At that point, the contender is not, the releaser is not a contender because it's not yet a member of the delay list. Second alternative, the choice of a successor might be delayed until the releaser has joined the list of those who are in contention for that machine. Third possibility is whenever an active transaction, no matter who it is, next tries to capture the resource, that entity gets the resource. So, for the software we've looked at, we have some of the software, Arena, which is the engine, or Simon, sorry, which is the engine, the simulation engine within Arena, ExtendSim. The successor is chosen at the instant the resource is released. So the releaser is not a contender for being chosen. Pro model, the releaser, the successor isn't chosen until the releaser has been identified as being in contention for the machine, as well as anyone else who's been in contention. GPSSH, AutoMod, and SLX, Simulation Language Extensible, behave in this third category. Now, is one of those types of, is one of those alternatives right and the other two are wrong? No, no. These are a matter of individual choices made by language designers. Furthermore, is this behavior the behavior you're necessarily committed to, given that you're using one of these languages? The answer there is no. There's also no. You can always, these are default behaviors for the simplest cases, the simplest design of model. Using the tools provided by given software, you can always model a given situation in a more knowing sort of way to achieve an effect that you're trying to achieve. But if you're not aware of these differences in the first place, then your model will probably not, under all circumstances, behave in the way that you are assuming it will behave. Situation 2. First in line is still delayed, but the next in line isn't. So some contenders need 1 unit of a resource, others need 2 units of a resource, and contenders of both types, if you will, are occupants of one and the same delay list. Well, if no units of the resource are available, and let's say the entity at the front of the delay list is waiting for 2 units, and the entity behind it is waiting for only 1 unit, and if 1 unit of the resource then becomes idle, what happens next? Situation like this, in other words, The waiting line might be ships waiting for tugboats. The ship at the head of the line might need 2. The ship behind it might only need 1. 3 logical alternatives here. Neither one claims the one idle resource unit. Both continue to be condition delayed. The guy at the front of the list can't get 2, so it doesn't take any. And the guy behind him isn't even looked at. Second alternative, the first entity claims the one idle unit, continues, however, to be condition delayed, waiting for another unit to be freed up. Third possibility, the first entity can't have everything it needs, so it doesn't take anything. The second entity claims the one idle unit and proceeds to make moves to use it, so that the service order is not strictly first come, first served. Which software and how? In the fundamental modeling approach, we've got 2 appearing in the first alternative row. We've got 2 appearing in the second alternative row, and depending on how you cut the cloth in GPSS, we've got 3 appearing in the third alternative row. Notice that ExtendSim appears in both the first row and the third row. So ExtendSim provides a checkbox where you can get alternative 1 behavior if you want it, and otherwise, taking the default, get alternative 3 behavior. So there is the concept of what are called contenders, where a contender is a condition-delayed entity that the software will consider transferring to the ready state in response to changes in the delay-inducing condition. It's not necessarily the case in all languages that each blocked entity waiting for a given type of resource will be considered to be a contender. It's a software designer's choice. In Simon, for example, only the entity at the head of the delay list is a contender. So if you're waiting for 2 and 1 is available, you don't take the 1, and nobody else gets it either. Nobody else in your delay list gets it either because they aren't even being looked at. In GPSS-H, all entities on the relevant delay list are viewed as contenders. Extend, as we've seen, can work either way. Situation 3, deliberately yielding control. We've discussed this state in terms of somebody watching the door into an estate sale situation and only letting people move through the door in groups of 10 people at a time. Typically involving a watchdog entity, such as the person monitoring the door into the estate sale situation. Or here, you might assume that units of units sized at, I should say batches sized at 10 units at a time are let move from an entry point to conveyor onto the conveyor, the goal being that those 10 units, for whatever reason in the logic of the system, are to be grouped together, form a group of size 10, and then let them onto the move through the entry point onto the conveyor. So this involves migration paths among entity states, and in particular involves that yellow arrow back to the ready state. So admitting ice cream cartons to a packing conveyor, one approach is to use a switch to model the entry point from the ice cream cartons, let's say, conveyor to the conveyor leading to the packing machine. The idea is to pack a common ice cream flavor into a packing box, 10 quarts of ice cream at a time. So when a carton approaches the entry point and the switch is closed, the carton is shuffled off perhaps to a user-managed list. A watchdog test the user-managed list at each clock time to see if there are now 10 cartons of ice cream on the user-managed list. When the test becomes true, the watchdog transfers all 10 from the user-managed list to the ready state and throws open the switch. Then yields control, says, I'm active, I don't want to be active anymore right now, put me down, push those 10 through the open switch, get back to me then, and I'm going to close the switch. Okay, so that is an attempt to provide that example. So how does the active entity deliberately yield control? GPSSH has a yield block. So does SLX. It's in the nature of ExtendSim with message passing. That yielding is the default behavior. Pro model, you force the watchdog to the future events list using a wait 0. A clock update phase then, without changing the simulated clock, will bring the entity back, the watchdog back eventually to the ready state, and from there it will become active. And Simon and Automod, you do this. I'm sensitive to the clock here. So we are at the end. I'm sorry, I had to go rather fast over those last several examples. So we touched upon these topics: the nature of discrete event simulation, the concepts of entities, resources, control elements, operations, overall projects, experiments within projects, replications within experiments, and then runs constituting a replication. The nature of entity management, examples, flowchart examples for one language, and why it matters, why it can matter for modelers to know how their simulation software works, especially, I think, in terms of interactive monitoring and not being blindsided by behavior of a type that you assumed would not be the default type of behavior. So the objectives: to introduce some of these ideas, to sensitize you, to motivate, hopefully to sensitize, hopefully to motivate, hopefully to enhance your eventual skills. And so I thank you for those of you who are still on board. Thank you very sincerely for your 2 hours of sustained attention. That is a long slog. We had talked about breaking this up into a sequence of 2 one-hour presentations. Maybe that would be something to consider for the next time, if there is a next time. Okay, Dave, over and out. Good luck to everyone in the audience with this, dealing with your life as a discrete event simulation modeler.
Thank you very much, Tom. I assume you do have a few minutes for questions if people want to hang around for that. Okay. Yeah, I do see one question coming in, but I did want to make one comment about this. When you and Dan were including Extend in this years ago, I'm trying to remember when that was. It was maybe 10 years ago or more. I think I counted somewhere in the neighborhood of 100 emails that went back and forth so that we could explain all these concepts. So right. There's a tremendous amount of work that's gone into this research and trying to fit the models that the internal models that those of us as software developers have into a theoretical model. And it's challenging from all ends because everyone looks at the same problem a little differently. So I hope everyone appreciates that. I do have one comment. Excellent topic for the model I'm building right now and for my current state of understanding of model building. Here's another question is, what is the software in your experience which covers the least amount of such common errors in their architecture?
Well, first of all, I think I would say I would be cautious about the use of the term error, because we're talking about situations where judgment has been exercised on the part of the designer of this software versus that software, and where differing choices have been made. I'm not sure that people would agree that there's only one correct way to do it when these choices for software design are being made. In some sense, maybe it would be nice if eventually the industry could arrive at some set of standards, but I'm not going to hold my breath for that to happen. As for software that, I guess maybe I would almost interpret the question as sort of in the following terms. If I'm really just beginning to get into discrete event simulation, which software do you think would be the easiest for me to digest meaningfully, while at the same time having an acceptable degree of flexibility in terms of the types of systems I can model? And I'll tell you, I really don't have an opinion on that. I know, well, I really, let me comment that the marketplace consists of about 50 different commercial discrete event simulation software languages. You can find these, there's a reference in the WSC Proceedings article to Jim Swain's survey that he conducts every 2 years and publishes in a monthly publication named ORMS Today. I think Jim's most recent survey was published in the November issue in 2011. So the various pros and cons for each of the approximately 50 different software systems out there are summarized in tables in that article, and I think I would refer the questioner to that article for further elaboration on what the answer, if you will, if there is one, to that question might be.
I have an additional comment, and obviously I am highly biased in this, but I'll step aside from my bias for a moment and say, look at the software that speaks to you. Everyone, like the software developers, we're making decisions as to what we think our customers will find most transparent. But look at it yourself and spend a little time with the software. I've had people say to me that X software is the class act in simulation, and it's something I've looked at and I frankly don't get. I've had people say the same thing about us. So there's a very strong element of personal preference there. There's no magic bullet, and you have to find what works for you.
Mm-hmm. Yeah. Also, if you're able to attend one of the annual winter simulation conferences, again given in December. As a matter of fact, if you go to Berlin this coming December, it's around the 10th of December or so, and the German Christmas markets are all taking place. Berlin could be a rather interesting place in December, in spite of probably the weather at that time of the year. But that conference is attended by quite a number of vendors. What would you say, Dave? Upwards of 20, 25 vendors?
Yeah, somewhere in there. Yeah.
Yeah, and you can go to any one of the vendor booths at any point during the 2.5-day conference and ask to have the software demonstrated for you. Or typically, the vendor is the person manning the booth does have demonstration software running anyway, in the very nature of things. So you can get a pretty interesting insight into a set of half a dozen, 8, 10, depending on your dedication, alternatives for discrete event simulation software. Some tend to be relatively special purpose, like modeling maybe conveyor systems, but most are quite general. Otherwise, what can you do? You really can talk to a vendor's representative over the phone, or maybe even schedule an appointment with such a person, if the logistics work for you. Not easy choices, I don't think.
Well, and another option is I encourage people to pick what they think an interesting part of their system is and send it to the vendor and say, can you model this? In our own defense, please don't ask us to model an entire end-to-end factory because we obviously have limitations on our time. But we have done that where we found the model was particularly interesting, and we're modelers too. We like doing this sort of thing. So if you pose an interesting problem to us, I can't imagine anybody in this industry that wouldn't leap on an opportunity to build an interesting model. I certainly enjoy doing it. So ask someone who's a professional to build that model for you and explain it to you and explain how it works. Take the time to learn a little bit about it, though. There's a lot of it's awfully easy to look at the pictures and say, oh, this looks nice for me. When if you're going to be the person constructing the model, you really want to spend some time behind the wheel, so to speak, and do that. So and
that.
I'm sorry. Go ahead, Tom.
That reminds me. There's the various countries in Europe, or maybe throughout the entire Eurozone, each have a national simulation society. And there's a publication called SNE, Simulation News Europe. It is, I think it's a quarterly. And they have an interesting series going that takes the following form. A person proposes a system to be modeled, describing it in all of the detail necessary to build the model. And then basically opens the challenge for others out there to use their favorite simulation language, if you will, in an attempt to model that system. And if the attempt is successful, and it usually is, then the corresponding work will be published in a follow-on copy or a follow-on issue of Simulation News Europe. I had the experience of posing a model that involved a canal and lock system that was based on a canal and lock system I had actually seen in Germany, and I presented at the same time as the problem a model for it in GPSSH at the time, and then it was very interesting to see how people weighed in with corresponding models and other software. And one of the things that I included in the description of the situation were a couple of what I call deterministic data sets, non-random data sets, designed to use a phrase, to dance on the nerve endings of the underlying logical situations that could come about. So anybody's proposed model could be checked out, that is verified, or at least moves could be made in the direction of verification by looking at the results the model would produce when deterministic data sets were used with the model. It really proved to be, for me, very interesting to see how that all evolved. That goes back, oh boy, that probably goes back 6 or 8 years by now.
I have one other very interesting question. I'll read it off to you. I was in a presentation from Jerry Banks long ago. He said that there has been a breakthrough in or advance in discrete event simulation technology, architecture, rather has advanced graphics issues that only confuse potential no users of software for discrete event simulation. He mentioned some products, but I'm not going to name names there. Do you agree with that comment? I actually have a follow-on comment for that too.
Oh, well, let's see. First of all, advances can take place below the level of the user interface that can have the effect of really enhancing the performance of discrete event simulation models in the sense of executing more rapidly than otherwise. An example of a context is the management of entities on the future events list. So when a newcomer is arriving, is being inserted into the future events list, what algorithm or algorithms are you using to determine the proper insertion point? Under Bob Sargent at Syracuse University, a student did a PhD dissertation in that area, for example. The development of new algorithms. Now, from the point of view of the user, that might be, fairly unexciting stuff. So my model will execute in only 80% of the time under this new algorithm that would otherwise be required under the predecessor algorithm. It may be sort of like a so what situation. Other possible improvements could take place at the level of the user interface, of course. And it's been a long time since graphical user interfaces have been introduced, and the ease of putting together the pieces for a model, whether you're getting the intended behavior or not, I think has been greatly improved. As far as Jerry's comment on graphics is concerned, I think my understanding is that he's referring to animation, the animation of simulation. And the animation, of course, is a chance to see selected aspects of your system, of your system's behavior and operation, on your monitor and in graphic type form. The impression that I am under, the pretty strong impression that I'm under, is that if a professional modeler is trying to convey to a person who doesn't really understand discrete event simulation, say a higher up person who controls purse strings and so on, wants to demonstrate what it is that can be done with discrete event simulation in terms of looking at alternative system designs and so on, that animation is a pretty powerful way to go if it's done appropriately. So I'm not sure that I, just offhand based on what Dave commented on, would agree with Jerry on that particular point. I don't know what Jerry had in mind if he's sort of dinging the use of animation in the context of simulation modeling.
I did have I'm sorry, Tom, are you done?
No. Mm-hmm.
I did have a follow-on comment that was I actually quite disagree with that, and I think that I could sit down and name a number of features that have been added in not only ExtendSim but other simulation software over the last few years. Just to throw out a couple, I know that AnyLogic has done quite a bit with pedestrian modeling, and that's a very new area and actually quite interesting. SLX has some really interesting features in it for modeling large-scale systems and is extremely efficient. That kind of goes back to a little bit what you said about something being efficient. But if you've got to model something that's really big, these could be the efficiency could be a very important feature, and the ability to decompose and kind of create your own simulation language within SLX is quite a significant advance. And then we've done work with modeling rate-based systems, high-speed modeling systems, where we actually combine discrete event simulation and linear programming, and that's all done under the hood. The user doesn't really have to understand linear programming or build a linear programming model to utilize it. So those are just three quick examples that I came up with off the top of my head. And I don't want to say that it's only us and those two other companies. I think every company is innovating in multiple ways. So some of it may not be as obvious or as flashy as animation, but it's certainly out there. So I would respectfully disagree with Jerry on that one.
Yeah, interesting. Also, it depends. When Jerry made the comment, if it was 10 years ago.
Yeah.
For example.
That's true. That's true. But I think that's been a continuous innovation that's been going on among all of the software developers, and I think anyone that fails to innovate will kind of tend to fade away a little bit. But
yeah, I think that my sense is that the competition is pretty severe out there, with upwards of 50 vendors competing for a piece of the pie. And if you go back to, I mean, I'm an old timer. I'm an old timer. If you go back to the time frame of the late 1960s, the first part of the 1970s, the degree of competition took the form of maybe 4 or 5 choices. So put a factor of 10 on that now. I mean, when there were only 4 or 5 choices, there was a pretty big piece of pie for everybody. With upwards of 40, 45, 50 contenders out there, it would really be interesting to know who has the biggest piece of pie and why. That is, what characteristics, both in terms of the software and in terms of the marketing, if you will, have led to them having the largest piece of pie. But if the average piece of pie is 2% of the market, chances are nobody has more than, what, 15% of the market, something like that.
Yeah, it's a hard number to calculate. And there's dollars, there's units sold, there's and if you include revenue for consulting, there's actually one question with many answers depending upon how it's framed. So
yeah.
And then the reality is, because most of the companies like ourselves are privately held and are not disclosing revenues, no one knows. No one has any idea.
Right. Yeah. Yeah.
I don't see any more questions, and we're a bit over time. Tom, thank you so much for taking your time out of your schedule to do this for us. We really appreciate this.
My great pleasure.
This is an excellent presentation. It will be available online. I will encourage people to review it, read the paper. There is, I understand, a new updated version of the paper being presented at this year's Winter Simulation Conference. So if you're able to attend the conference, I think it's good to review this. So thank you again, Tom, and I will end the session.
Okay, great, Dave. Thank you. And
okay.
Thanks to everyone who looked in on the webinar in any way, shape, or form.
Okay.
And good luck. Good luck to everyone.